In problem 11.69, you're given that you have a voltage source over here, which is equivalent to 440 volts RMS, and it cycles at a frequency of 60 Hertz. It also has a load over here, Z, of 20.J15 ohms. And you're asked three things for this particular problem. Number one, what is the power factor? Two, what is the average power dissipated by this load? And then part 3 asks, what is the value of a capacitance, so we show this capacitance here, that could be added to the circuit that will give a unity power factor. Okay, so let's go ahead with the first part here. In part A, to find the power factor, what we're first going to do is find the complex power S. And the complex power S is given by the RMS voltage squared divided by the conjugate transpose of the load Z. And so we have 440 volts RMS. We can square that quantity and divide it by the conjugate transpose. So all we have to do to get the conjugate transpose is just change the sign, S-I-G-N, of this plus J15 to a minus J15. And so we put that in here. And then in order to get the complex pair out of the denominator, what I'm doing here is just multiplying by the complex conjugate of the 20 minus J15. So the complex conjugate is going to be 20 plus J15. We multiply that on through, and we get the quantity that you see over here, 3872000 plus J 2904000 divided by 20 squared plus 15 squared. So what this does is it now gets it so that we just have a single complex pair. You simplify that on down, and so S is given as 6195.2 plus J 4646.4. And so this is S. In your textbook, this would be given as a bold S. That is going to be an S that we can express as a phasor. And so the apparent power is going to be the magnitude of that. And so we can find the magnitude of that just by taking the square root of the sums of the squares of the real and the imaginary components. That works out to 7744. And then the real power, P, is equal to the real part of our S. And so if we work this on out, going back up to here, the real part is just equal to the 6195.2 that we had over there, or you could go back to this and just say, okay, that is this portion divided by the sums of the squares down there. So 6195.2 is the real part, and the power factor is going to equal the real power divided by the magnitude, or the apparent power, the magnitude of S. So that's going to work out to be just 0.8. 6195.2 divided by 77.44. And you can also determine, is that leading or lagging? In this case, it's lagging because if you go back up to the complex pair, you notice that the imaginary component is positive. And so if you think about leading versus lagging, if you think about those as vectors, if you have a positive imaginary component, that is lagging. If you had a negative imaginary component, that would be leading. Okay, so that solves for our power factor of 0.8, and the average power delivered turns out to be just the equivalent is the same as the real power, P, so that is just 6195.2 watts, or 6.1952 kilowatts. Now, moving on to part C, in order to do some power factor correction, we want to add a capacitance in parallel. And the idea here is that we want to get our current and our voltage exactly in phase with one another. And in order to do that, we want our effective load to be equivalent to just a real load, a resistive only load. And that way, we want to be able to counteract the complex portion, the imaginary portion in the complex pair. So currently what we have for our load is 20 plus J15 ohms. And we know that the impedance of a capacitor is going to be given as 1 over j omega c. Now if we go back up to what we know about this particular voltage source, we're told that the frequency is 60 hertz. So from that we can find our omega value is just going to be equal to 2 pi f, so our omega is going to be 120 pi. So if we plug that in to figure out the impedance of the capacitor, that's just going to be 1 over j, omega being 120 pi, times c, or if you want to get the j out of the denominator, it's going to be negative j over 120 pi times c ohms. Now, what we want is to have a parallel equivalent of the capacitor impedance and the load impedance that we already have to have no imaginary part. So if we go about trying to find a parallel equivalent, we go 1 over the current load plus 1 over the capacitor impedance. So we could just write this as j times 120 pi c over 1. That's just flipping upside down what we already have here. And so if we work this on out, we can get a common denominator of 20 plus j15. We can just take this, multiply it by 20 plus j15, leave the 1 plus that times 20 plus j15 in the denominator. The common denominator now becomes the numerator, and so we get this. And then we can go ahead and multiply on through. And so here's what we get here, putting together our real terms, putting together our imaginary term in the denominator. Now what we want to do is multiply the equivalent impedance by the complex conjugate, top and bottom. And so here I'm just multiplying by the complex conjugate of the 1 minus 1800 pi c plus j 2400 pi c. So here complex conjugate, just put in the negative. And so now I get down to here. What this is going to do is now have a completely real denominator. And so now I'm getting together the real portion here in the numerator and the imaginary portion. I don't have to go through solving the rest of this. All I know is that I want my imaginary part to go to 0. So in order for that to happen, this scalar multiple of j needs to go to 0. So 15 times the quantity 1 minus 1800 pi c minus 48,000 pi c has to go to 0. So I can go ahead and multiply this by 15, leave that on the left side, and shift all these negative values over to the right, and I can get together and realize that that is going to work out to be the total of 75,000 pi times c. So I divide 15 by 75,000 pi, and I end up with a capacitance of 0.000063662 farads. And so if I move my decimal place to the right 6 places, that works out to be 63.662 microfarads. And so that's how you can figure out a capacitor that you can do power factor correction with in order to make all of your power real, and so you're not wasting power in the quadrature region.